In this lesson, we're going to be looking at the areas of some of the lesser known formulas for quadrilaterals: trapezoids, rhombuses, and kites. Now, theorem 10.4, the area of a trapezoid, states, the area of a trapezoid is half the product of the height and the sum of the bases. And the way that this one works is that if we were to take a trapezoid, like the one shown, and cut it in half at its mid segment, take this top half and fold it down, what we would end up with is a parallelogram whose base is the sum of the two individual bases, but half as tall. Or what you could think of it as is we're finding the average of the two bases, basically forcing our trapezoid to act as a rectangle, and rectangle is base times height, so we need to find that average. Let's take a look at how we can find some actual areas based on the state of Nevada. Its shape is relatively that of a trapezoid. The two bases are 205 miles and 511 miles, with a distance between them of 309. So in order to calculate the area, rough area of the state of Nevada, our area is 1/2 our height and the sum of the bases. So substituting in values, we have 1/2 of 309 times 205 plus 211. Remember, the bases are the sides that are parallel to each other, and that should have been 511. So we have 1/2 of 309 times the sum of these bases is 716. Now multiplication is commutative, so I'm going to take half of the 716, which is 358, and multiply that by 309, giving me a total area for the state of approximately 1,396 and 2/10 miles squared. Now, when we're working with trapezoids, we also run into the situation where we might have parts that are not labeled, but we can use our trig identities and ratios that we've been working with in order to find those. So here we have a trapezoid on the right with bases of 5 meters and 7 meters. Well, if we find the average of 5 and 7, that mid-level system will be 6 meters. Next, we need to find the height. Well, if we were to sever off the part on the end that makes it a trapezoid instead of a rectangle, this would have a length of 2 meters. And what we would have is a 30, 60, 90 triangle, meaning that the hypotenuse was 4, and then that height would be 2 square root of 3. So multiplying our numbers together, area is 1/2 the sum of the bases times the height. Sum of our bases was 12, half that was 6, so we have 6 times 2 square root 3, so the area is 12 square root 3 meters squared. So that covers our trapezoids, different ways that we can use the information to get it. Now we need to work on our kites and rhombuses. So the area of a kite or rhombus, which is theorem 10.5, is half the product of the lengths of the diagonals. So what this means is, as we're looking, area equals 1/2 D1 times D2. And those diagonals are typically always shown or can easily be found. Now, bear in mind a rhombus, one of the subgroups of that is a square, so we could also use the same method for a square if we don't know the length of one side of that square. So let's take a look at how we can apply this one into a situation. We have shown a rhombus, or sorry, a kite with semi-axes of 3 meters, 2 meters, 3 meters, and 5 meters. In order to find the area, we're going to have to use area is 1/2 diagonal 1 times diagonal 2. So we need to find out what those full diagonals are. The two parts of the semi-minor axis, which is this one, the shorter of the two, 3 plus 3, so that entire distance is 6. So we have 1/2 of 6 times the length of the major axis is the 2 plus 5, or 7. So half of 6 is 3, 3 times 7 is 21, so we have an area here of 21 meters squared. So the rhombuses and kites actually work out pretty nicely. You just have to remember that it's half of the product of those diagonals. So some new formulas here for you perhaps. Make sure you have them copied down, ready to use, and be ready to use them as we do move forward.